Example M7.6, express the linearly distributed load acting on the beam between A and B with discontinuity functions. Okay, so we are yet again presented with another dilemma that branches out on the uniformly distributed load that is discontinuous on a span on example M7.5. Okay, so if we pass a cutting plane here, it would not be hard for us to determine the loading function in terms of x, okay, because it's not discontinuous, okay, it's from A towards the cutting plane. But when we reach this cutting plane, however, there is a discontinuity, okay. So the thing to do here is, again, what we will do is we will extend this like in the previous example. We will extend it here, okay, we will extend it here, but then we have to match it with a load going up here, okay, going up here. Not as easy as it sounds, right? Okay, so what we're gonna do here is we're gonna find out how we can go ahead and do this and express this in terms of discontinuity functions. So our first instinct would be to represent the linearly distributed load on the beam with just a single term. However, again, when we move on the segment from B to C, there is a discontinuity, and therefore we have to take that into account, okay. So this is supposed to be 2.5, okay, minus 2.5. Minus 2.5. Okay, so moving on. The sum of these two expressions represents the loading shown next here, okay? So it's basically only a rectangular load, okay? So what we're doing here, instead of just adding on to here, all right? So we're just extending this here. We're just extending that here. What we're doing is we're breaking it down into two loads, okay? So what we're gonna do is we're gonna take this load and break it down into two loads. So we have a triangular load rather, okay? A triangular load going up, and one going up and one going down, and two rectangular loads going down and going up. All right, so this is the train of thought that we are trying to follow. All right, so you may be wondering why this is 50 over 2.5. Again, this represents the slope of the load diagram, okay? So you can represent that in terms of 50 over 2.5, okay? So that is 50 over 2.5. The sum of these two expressions represents the loading shown next, okay? So we have here, okay, this term here, this is the first term, and this is the second term. All right, now adding these two will result in a beam looking like this, okay? There is still a rectangular load here, all right, because you canceled out the triangular load with respect to this and this, okay? So what's left is the rectangular load, and to cancel out this rectangular load, you have to add another rectangular load but in the opposite direction, okay? So that will add onto our expression for the uniformly distributed load, okay, for the distributed load rather. So then we have negative 50 kilonewton meter over 2.5 times x minus 0. This is supposed to be 2.5 again to the 1. Okay. And then plus 50 over 2.5 times x minus 2.5 to the 1. Then we add, okay, this third term here, 50 times x minus 2.5. All right. And we will come out with this equivalent loading. Okay. So it's just adding on. Again, it's just adding on so that you can cancel out the added load. Okay, let me rephrase that. It's adding on to the existing load and then canceling that out by opposing it with an equal but opposite force, equal but opposite in direction distributed load. All right, so I hope that's clear. Basically this is the expression for the loading diagram, and we see that this is negative 50, positive 50 over 2.5, positive 50 over 2.5, and positive 50. Okay, so again, this refers to the slope of the beam, the slope of the loading diagram. Okay, and this is the opposing loading, the slope of the opposing loading diagram. Okay, and this represents this the rectangular load going upwards. Okay, so I hope that's clear. In the next video, we'll be tackling yet another beam concerning discontinuity functions.